So Diego Gomez was unfortunately not able to attend, so I'm filling in for him. My name is Dave Renaud. I'm from the University of Guelph. Diego made this presentation, and he had no financial disclosures to make at any point in this presentation. So as all of us in the room know, diarrhea is a really common disease that's affecting neonatal dairy calves. And often these calves can go on to die, and they die from dehydration. They die from acidosis, they die from hyperkalemia, and also cardiovascular and renal dysfunction. If you specifically look at metabolic acidosis, and you look at traditionally how it's been diagnosed, it's through the use of bicarbonate and also base excess. And however, one of the more recent studies that's looked at it, this was one of the papers published by Dr. Gomez and his team, looked at the effect that like sodium and chloride, as well as unmeasured strong ions, and as well as weak acids, really have an effect on the level of dehydration and also death in calves. So with metabolic acidosis being so important in its importance to correct it, obviously you want to try and do it through oral or intravenous solutions. And if you look at some of the literature coming out from humans where they looked at the intravenous fluid therapy, a lot of the metabolic acidosis is corrected through crystalloid fluids. And if you look at the content of the intravenous fluid, it's really important to have high levels of sodium compared to chloride. And that will lead to an alkalizing effect, which is seen at this top line here, which is sodium bicarbonate. If you have similar levels of sodium and chloride, that will lead to an acidifying effect, which is seen on the bottom portion, which is a ringer solution, where it will gradually decline over time. If you look specifically at calves in oral rehydration therapy solutions, one of the recent papers that was published looked at the effect that sodium bicarbonate and also sodium acetate had for the treatment of calves with naturally acquired diarrhea, and looking at the correction of acidosis and purely looking at it from the correction of bicarbonate. And both solutions were actually quite effective at correcting the levels of bicarbonate and increasing it over time to correct the metabolic acidosis. The challenge is that there really isn't a lot of data in regards to the use of intravenous sodium acetate, and that's where Diego and his team really went and focused on. So the objective of this project was really to understand the underlying mechanism that are responsible for changes in blood pH and bicarbonate after the infusion of two different alkalizing electrolyte solutions to healthy calves. And this all was done using the physiochemical approach of the strong ion difference. How they did this study was as a prospective study. They did a Latin square design with 5 healthy calves, which were infused with the 2 different solutions, the sodium bicarbonate and sodium acetate, over a period of 2 weeks, with each animal receiving 1 infusion per week. So what they did was they gave 1 liter of each solution intravenously at a constant rate of infusion over a 1-hour period, and they had 2, obviously, treatments, sodium bicarbonate and sodium acetate, which were the 2 treatments in this study. They then took arterial and venous samples over time. They took it before treatment, 20 minutes and 40 minutes after treatment, and that was just for arterial samples to measure pH and bicarbonate only. They again took it at 60 minutes, 90 minutes, 120 minutes, 180 minutes, and also at 300 minutes to really see what the changes were over time. For arterial blood gas, what they looked at was the partial venous carbon dioxide levels, the pH, bicarbonate, and also base excess, so it was calculated by the blood gas machine. They also looked at plasma sodium, potassium chloride, and L-lactate, and measured total protein. And through all the strong iron differences, which I'll show in a second, this is how they calculate it using the formulas that are at the bottom of the screen. The data was analyzed using a 2A ANOVA, which was based on the Latin square design, and they had 2 independent variables that were put in the model, which were the experimental infusion, so whether it was sodium bicarbonate or sodium acetate, and also the time of the infusions as well. They also monitored for any clinical signs that were changing over time. And none of the data was really significant in the clinical data, which included the heart rate, respiratory rate, temperature, central venous pressure. And also they looked at an electrocardiogram, which was measured at 10-minute intervals. And there's no differences between the sodium bicarbonate or sodium acetate groups. If we move into looking at changes in arterial blood pH, you'll see that both groups had a really similar effect, where we have arterial blood pH on your y-axis and the time on your x-axis. So both, significantly increased the level of the arterial pH, where it went up and peaked at about 90 minutes after the infusion, and then went down over time, almost to about basal levels by the end of the sampling time period that they looked at. And there's no statistical differences between the groups. They also looked at changes in the plasma bicarbonate levels, and as you can see, they're very similar to the arterial pH, where they went up significantly over time to the 90-minute time point, and then they dropped gradually over time, but they never returned to that basal level like the arterial pH did in the last slide. And there was no statistical differences that are found between the two groups of sodium bicarbonate and sodium acetate. When we look at changes in the plasma strong iron difference, again, very, very similar effect in both groups, where they increased substantially over time to 90 minutes, and then they gradually declined over time. And there's no statistical differences between either sodium acetate or sodium bicarbonate. And if we dive a little bit deeper into why this happened, why do we see these strong iron difference changes? And we look specifically at plasma sodium and plasma chloride. A lot of it was driven off of these changes in the sodium and chloride levels, where again we had those increases in levels of sodium to about 90 minutes in both groups, and decreases in levels of chloride. And the level of sodium, which is interesting in both groups, remained elevated for the rest of the sampling time points in the sodium bicarbonate group, whereas in the sodium acetate group it declined a little bit. And so there's a little bit of significance at the end time periods between those groups. If we look at the changes in the rest of the strong iron difference, or how it's calculated, and focusing on the weak acids, which is mainly looking at albumin, there's no differences found between groups, and very little changes that occurred over time with respect to either treatment. If we look at other unmeasured strong ions, which is mainly D-lactate, there's a mild elevation in sodium bicarbonate. I think that group had a 1 millimole per liter higher than the sodium acetate group, but clinically I don't think that would have a tremendous difference between the two groups, and the rest of the time points were not significant. Okay, so if you look at how the traditional approaches look at metabolic acid-base balance through the Henderson-Hasselbalch equation or through the base access, they explain a lot of the alkalizing effects of these solutions mainly through the changes in the level of bicarbonate. So providing a bicarbonate or providing a bicarbonate precursor would result in those changes in the blood pH. But if you look at acetate, specifically looking at sodium acetate, it's not a precursor for bicarbonate in any one of their functions that it has. So acetate's a precursor for energy and glucose as well. But at no point into how acetate's used does it actually change over into bicarbonate. So I think a lot of the changes that are resulting in the levels of arterial pH, as explained by the strong iron difference, is through the alkalizing effect of the solutions where we have high levels of plasma sodium relative to chloride, and we have relatively little or no impact on plasma protein unmeasured strong ions. So I think the sodium acetate effect is really through increasing the level of sodium and not having an impact on the levels of bicarbonate. With that, I'd like to acknowledge the sponsors of the research, the Ontario Veterinary College, the University of Guelph, and the University of Florida, and I'll take any questions you guys have. Thanks.